8.3, graphing reciprocal functions. Here's the objective. Reciprocal functions. You should write this down. All reciprocal functions can be written in the form of f of x equals 1 over x, or y equals 1 over x. Here you can see the graph of the reciprocal function. This particular graph is called a hyperbola, and we'll talk more about hyperbolas in another chapter. But they've got these two curves, these are like branches, and then you have asymptotes. So let's go ahead and jump down here to the asymptotes. This particular mother function or parent function, the asymptote would be the y-axis and also the x-axis. So that means that your asymptotes are x equals 0, that's your y-axis, and y equals 0, which is your x-axis. Notice that you do not have any y-intercept. The graph will not cross the y-axis because it's approaching the y-axis, and both from the left and from the right. Now your domain and your range are both going to be all non-zero real numbers. Now that doesn't mean you're going to write that down every single time when you have a problem. We'll talk about what that means with the examples. Okay, this example is asking us to determine the values of x for which this function is not defined. You may recall that we did this in section 8.1. So the function is going to be undefined whenever your denominator is equal to 0. So we're going to set the denominator equal to 0. To solve this quadratic equation, we are going to factor it. That factors as x plus 8 times x minus 3. And then you set each of those equal to 0. You're going to get x equals negative 8 or x equals positive 3. So the function is undefined when x equals negative 8, or actually let's say and x equals positive 3. Here's your first video quiz question. Example 2. This question is asking us to identify the asymptotes, domain, and range for this function. So this is directly related to the where your function is undefined. So it's going to be undefined whenever your denominator is equal to 0. So we're going to set the denominator equal to 0 and solve, and you're going to get x equals 2. This means that you're going to have a vertical asymptote at x equals 2. Let's take a look at what that means graphically. If you were to draw on the line x equals 2, let's see if I can get my pen right there on top of the 2. Do you see how the graph approaches that x equals 2 asymptote from the left and from the right? That these branches are approaching that asymptote, which was not drawn in until I drew it. Now, you're going to have a horizontal asymptote also. Now, you can see it graphically. What you're looking for your horizontal asymptote is as x is approaching positive infinity and as x is approaching negative infinity. This should sound familiar. We talked about this last semester. So as you move to the right, do you see how that branch is approaching the x-axis? And also as you move to the left, that branch is approaching the x-axis. So that means that you have a horizontal asymptote on the x-axis, and the equation for the x-axis is y equals 0. Now let's talk about the domain. We said in that chart that the domain and the range are going to be all your non-zero real numbers. So let's talk about the fact that your domain is not going to be everything because you've got that vertical asymptote. Remember, your domain is your x's, so your left and your right. So your function is defined almost everywhere except that you have to jump over that vertical asymptote. So we're going to say that our domain is going to be all reals not equal to 2 in this case because your vertical asymptote is at 2. And then we're going to say that the range, okay, and your range is your y's. So thinking about it, the bottommost value to the topmost value. So this time, and actually let me go ahead and draw in the horizontal asymptote here, right there on top of the x-axis. So when you're thinking about looking at this graph vertically, the graph is defined everywhere except for that horizontal asymptote. So your range is going to be all reals not equal to 0. I'm going to put a little colon here for the range. Let's put one in there for the domain. Okay, so your domain is all reals not equal to your vertical asymptote. Your range is going to be all reals not equal to your horizontal asymptote. Let's do another example. Let's first find where the function is undefined. So you're going to set your denominator equal to 0, so x plus 2 equals 0, so x equals negative 2, and that's going to be your vertical asymptote. Okay? Your horizontal asymptote, I'm going to tell you a little trick this time. Do you see in the equation that you have 1 over x plus 2 plus 1? We didn't have this in our last example. There was nothing there, so you can assume it was a plus 0. That is your vertical asymptote. So your vertical asymptote is going to be y equals 1. I'm sorry, I said vertical, I meant horizontal. That's going to be your horizontal asymptote. Okay, so once again, to find the vertical asymptote, you're looking at the denominator, you're going to set that equal to 0, and then here, this plus 1, that's going to be your horizontal asymptote. And both of these things, of course, are related to your domain and range. So the domain, in this case, is going to be all reals not equal to, since you have a vertical asymptote of negative 2, it's going to be all reals not equal to negative 2. And then your range is going to be, I'm going to start abbreviating a little bit more, all reals, and I'm just going to do an equal sign with a slash through it, not equal to 1. So not equal to 1. Here's your first, or your second video quiz question. And your third. Okay, this slide should look familiar because I showed you the almost identical slide from section 7.1 on graphing exponential functions. So the difference being, of course, that here we're graphing reciprocal functions. So you'll notice that, for example, k is your vertical translation. So this number that's being added outside the function is your vertical translation, and that relates directly to your horizontal asymptote, just like with exponential functions. And then h is your horizontal translation. So h is the number that's being added or subtracted to the x of the function. And that's going to be related directly to your vertical asymptote, because obviously if you just set x minus h equal to 0, that's going to give you your vertical asymptote. And then the a is going to affect the orientation and shape of the graph. And again, it's going to reflect if it's negative, and then it's going to affect it vertically, and it's going to affect about how fat and how skinny the graph is going to be. All right, so let's do some graphing. So this example, we're going to graph it, and they ask you to state the domain and the range. I'm going to go one step further, and I'm going to identify the horizontal and the vertical asymptote. I'm just going to abbreviate vertical asymptote V dot A dot. So you're just going to set the denominator equal to 0, x plus 1 equals 0, so therefore you're going to get x equals negative 1 for the vertical asymptote. The horizontal asymptote, as I said, is going to be this number that's added outside the function. That's your vertical translation, or your horizontal asymptote, so that's going to be y equals 3. I'm going to go ahead and draw these asymptotes. So x equals negative 1, that's going to be this line here. Draw that in with a dashed line. Remember, asymptotes are always dashed. And y equals 3 is going to be this horizontal line here. Now, to complete the graphing, I'm going to graph this function in my calculator, and I suggest that you do the same. Okay, I went ahead and wrote down some values, because what you'll notice in your calculator when you graph this is that your calculator is going to say error when x is equal to negative 1. And that's because you have a vertical asymptote there. The function is not going to be defined when x equals negative 1. But when you write down your t-table, you should not write down the word error, because that's not proper mathematics. You're going to write down undefined. And so I tend to put the vertical asymptote in the middle of my t-table, and then I'm going to plot points on either side of it. So I notice that when x equals 3, y is 3.5, and so on. Okay, I went ahead and completed some values here. So we're going to plot these points. I'm going to go ahead and plot them. Okay, they're plotted, and they don't look like much, but remember, you want to use your asymptotes as a guide as to how close to your asymptote you're going to be, and of course you want to approach those asymptotes, draw arrows on the end of it, and there's your graph. We also have to identify the domain. So the domain, remember, is going to be all reals not equal to negative 1, because that's where you have a vertical asymptote. Your range, whoops, misspelled range, is going to be all reals not equal to 3. Let's do another one. So the vertical asymptote, set the denominator equal to 0, that's going to be x equals 2. Horizontal asymptote, looking at the number there on the outside of the function, y equals -1. Draw your asymptotes. X equals 2 is here. Y equals -1 is here. Type this into the calculator and go to the t-table. We have a vertical asymptote at x equals 2, so it's going to be undefined there. And then our other values are 1, 3, -5, and -3. Plot those points, and then use those points and the asymptote as a guide for how to draw those branches. Remember to put arrows on the end of them there. And then, of course, we need to identify the domain and the range. So the domain is going to be all reals not equal to 2. The range is going to be all reals not equal to -1. Here's your 4th video quiz question. And our last example. We have a commuter train with nonstop service from one city to another with a distance of about 25 miles. We're going to write an equation to represent the travel time between the two cities as a function of rail speed, and then we're going to graph the equation. So, since we're talking about distance and rate, we need to use the DIRT formula. Distance equals rate times time. And the distance is 25 miles. So we have 25 equals rate times time. And it says to write an equation to represent the travel time, so that means that we need to solve for t. So we're going to have 25 over r equals t. So that's the function that we're going to graph. To graph this function, we need to identify the asymptotes. So the vertical asymptote is going to be whenever your denominator is equal to 0. So that's, of course, when r is equal to 0, or I guess we could just call it x equals 0. And then your horizontal asymptote, since there is no number on the outside of the function, that's also going to be whenever t or y is equal to 0. I guess technically we should change these from x and y to rate and time. Oh, that's supposed to be a t. Let's try that again. T. There we go. Now you're going to go to your calculator, you're going to graph this function and make a t-table. There's my t-table, and I'm going to plot those points. Oh, and I'm going to plot the asymptotes first. Let me do my asymptotes first. So I have an asymptote on the x-axis, or the r-axis, and an asymptote on the y, or the t-axis. Alright, now I'm going to plot those points. So -2 and then -12.5 is about right there. -1, -25 is right there. I have an asymptote at 0, and then 1, +25 is here, and then 2, 12.5 will be about right here. And of course, again, use your asymptotes as a guide. And of course, you can also look at the other values in your t-table to plot additional points if you feel that's necessary, if you want to be more precise.